we have shown that this matrix is the Jacobi and Gauss-Seidel converge for various situations. So the next question is, how fast do they converge? So before we get to that, let's actually switch gear a little bit, switching from math to some implementation and show some examples of how fast Jacobi and Gauss-Seidel converge. So to get us a little bit of so to do that, let's actually solve a Poisson's equation again. Okay, so how many grid points would you like to start with? 100. So I want to do the way without ever constructing a matrix, right? So let's go back to our Jacobi and Gauss-Seidel implementation. So we have the formula of both Jacobi up there and the Gauss-Seidel down here. And let's just pick a b equal to 1's n and 1. So my b is going to be the uniform matrix. All right. Okay, and I want to start an x is equal to 0's, n and 1. So here we have a grid consisting of 101 intervals with 100 interior grid points. So my dx is going to be 1 divided by n plus 1, right? So that'll give me everything I need to evaluate both of these formulas. To implement Jacobi, I also need a vector to store the previous iteration. So if you look at this equation, I only need to have xk and xk plus 1 in memory, right? I don't need any k minus 1, k minus 2's. So in memory, I'm just going to say my x is xk plus 1 and x0 is my xk. Okay, and then what I will do is, let's just do one iteration to get started. So the one iteration would be the following. So first of all, my x of 1, my left side, because I don't have any xi minus 1 at that grid point if I is equal to 1. So this is going to be 0. So this is just going to be x0, so that's this one, at 2 divided by 2 minus dx squared over 2 times b1. So that's my first grid point. And then I'm going to loop for r equal to 2 to n minus 1, right? Because at n, I also have a special formula. I don't have I plus 1 anymore. I'm going to say my xi is equal to x0 of I minus 1 plus x0 I plus 1 divided by 2 minus dx squared over 2 times bi. That completes the iteration for all the interior points. And my xn also has a special formula, x0 of n minus 1. I only have the left neighbor as opposed to the right neighbor, times bn. Okay, so that completes one iteration. So let's plot x to see what I get. Why do I get zeros? Wait, my b's is 1's. Xi is equal to, that doesn't make sense. So this formula, my x0s are 0, so this shouldn't be anything. My dx, what is my dx? Dx is non-zero. Dx squared divided by 2 times b should be non-zero, right? What is x? 1. No, my x is actually non-zero. So, wait, is B a matrix? No, B is. So why did it show my x to be 0? So my x, yeah, my x is not 0. If I plot my x, why does it think my x is 0? Oh, yeah, it's not 0. It's just a weird range, right? It's actually a very small negative value. Right. So that's one iteration. So let's perform several iterations. K goes from 1 to 100. So let's perform 100 iterations. And for each iteration, I'm going to set x0 equal to x. That's important. Sometimes I forget that. And my x1 to xn, I'll do the same. I'm going to evaluate and end. So that completes 100 iterations. And let's plot it. Okay, now I get something not really 0, right? It's pretty small. Okay, so let's actually hold on to see what I get for k equal to 1,000. So let's perform another 1,000 iterations. Evaluate. What did I do? For I think I didn't just press enter. I think. Okay, so now I did 1,000 iterations. Plot it. Right. So 100 iterations, 1,000 iterations. They have been updated a lot, right? And then let's perform. So that means if x keeps changing, that means I haven't converged. Now let's do 10,000. Evaluate. I want to plot again. Right, I get another factor of change. So my solution probably still haven't converged. Let's do another 10,000 iterations, right? So from here to here, evaluate. I'm gonna plot. Okay, now I get two axes after 11,100 iterations and 21,100 iterations. The solution are the same, right? So okay, so basically my Jacobi iteration has converged. So for many of you, I believe this is more iterations than you anticipated, right? So Jacobi iteration converges very slowly for the Poisson system. That's kind of a known fact. And what's a little bit more surprising, perhaps, would be, what do you think if I increase the grid points from 100 to, let's say, don't be too aggressive, 200?